Hello, class. I'm doing the recording for section 5.2 for statistics. It covers mean, variance, and standard deviation and expectation. And this is in your workbooks right around 130 or so. Okay. Okay, so first of all, it talks about a review of chapter 3 material when we took our test number 1 over chapter 3 material. It talks about, it reminds you how you were dealing with raw data, which is going to change for this chapter that we're in, chapter 5. And it reminds you of some of the formulas. So one of the formulas we covered was the sample mean. So the sample mean is x bar, summation of x over n. So that was one of the formulas there was 2 that you could use, and this is one of them that I suggested that you make use of. We really didn't have a population mean that we calculated any calculations for. Generally, we worked mostly on sample means. And we didn't have any population variances that we computed, but we did work on sample variances. And I believe we used this formula, which was the shortcut formula. And you had to demonstrate that on your test number 1 for chapter 3. And then you were supposed to verify that on the calculator, take the standard deviation and square that. Okay. Now, what's going to happen is that in chapter 5, we're dealing with discrete random variables with corresponding probabilities, and it's not raw data. So there are discrete random variables, which they call X, okay? And then the probabilities, they refer to them as P of X, okay? And so the formulas also, notice how for chapter 5, we will be using Greek letters. This is the Greek letter mu. And also the variance. Let's see. I'm going to do this. I'm going to put brackets around this here. So they're taking the random variables times each probability, and they're going to sum that up. And this is going to be in units. If you have to label with some kind of units, whereas the variance is using units squared. And the symbol for variance is actually summation squared or summation squared sub x, okay? And I'm wondering, I will have to look that up. We're going to use the calculators. We won't do it by hand, but because of the way this is, what this is saying, I'm wondering if this should have been an equal sign, because this is the formula for variance. I think that should have been an equal sign here. Yeah, I think right here, this should have been an equal sign, because that's the symbol for variance. And then it's equal to this. And they did put the brackets around here. Probably should have had like another set of brackets around here is probably what they should have had. There's a little set here. But we're not going to compute them by hand. We're going to use the calculator on that, but still. And then, so this is the Greek letter sigma. This is sigma, so that's sigma squared. And then standard deviation, they left that off. Over here, they have standard deviation over here, but this is for test number 1, chapter 3, when they had raw data, and they said the formula was square root of s squared for that. So the standard here, the sample standard would have just been S then, or this is S squared for variance. Okay, so here, standard deviation is going to be just sigma, or you can call it sigma sub x. And this is equal to the square root of sigma squared. And when you get this, this is going to give you, this is in units. Okay. So it says that there is a rounding rule also. The rounding rule for the mean and the variance and the standard deviation are all the same. Should be rounded to one more decimal place than the outcomes of x. So remember, x is here. This is like, for example, this problem is the number of trips. Notice how these are predominantly whole numbers. These are whole numbers. So if you round one decimal place, you're going to round the mean to the tenths place. One decimal place beyond how this is listed. When fractions are used, they should be reduced to lowest terms. Okay, so we kind of know that from chapter 4 on probabilities. Fractions are always reduced to lowest terms. The other thing, though, is money. There is an exception for money, except for currency problems. Currency, money problems. Except for currency, money problems, it's preferred to round to the hundredths place. Hundredths place is the nearest cent. Okay, now when we put this information in the calculator, we're going to put L1, X random variables, and list L1 and L2. We're going to list our probabilities in L2. And for the calculator, let's see, rounding to the tenths place. And this is because, why? Because the X random variables are whole numbers. So that's why you round one decimal place beyond that, okay? And on the TI 84, we're going to use the calculator for these, and when we find the mean, we're going to find the mean using the TI 84 and looking at X bar. So they don't change it. The calculator doesn't know how to change it to mu. So unfortunately, we just look at the X bar. But when we write our mean will be written as mu for the mean, not X bar. And we'll round it to the nearest tenths because this is not a money problem. This is saying that the probability distribution shown represents the number of trips of 5 nights or more that American adults take per year. That is that right here, 6%, this is your 6%. They change it to a decimal, 0.06. 6% do not take any trips lasting 5 nights or more. So you see it's a 0 there. 70%, so make it 0.7, take one trip where they last 5 nights or more. And then 20%, they take 2, right? Number of trips, 2 trips that last 5 nights or more. And then 30%, is that right? Oh, that's 3%, not, that's 3%, so 0.03. So 3% take 3 nights or more, or 3 trips. Number of trips, they take 3 trips lasting 5 nights or more. And then only 1% took trips, took 4 of them, 4 trips where they last that long, 5 nights or more. So in the calculator, you're going to use stat and edit. Okay. And so go to that calculator. Stat, edit, enter. Okay, so you're going to go up to the top and clear, and enter. Oops. So go to the top, clear, enter. Okay, over here, tab over here, go to top, clear, enter. Okay, and then you're going to start inputting your data. Okay, then you're going to go to then you're going to go to stat. You're going to tab to calculate. So stat, tab to calculate, and then you want one variable, stats, then hit enter. And then your list is going to be L1, and your frequency list is going to be L2. So you want to hit the second button and number 2, because that's where L2 is at. Okay. So you're going to hit the second button and number 2, because that's where L2 is at. And then just tab down to calculate. And then hit enter. And remember, you're going to look at X bar, which is 1.23. And then you're going to round to the nearest tenths. And look at the neighbor. Is the neighbor 5 or more? Nope, that's the 3. So mu is about 1.2. Okay. All right, so this is what we're going to repeat for the next problem. Next two problems, we're going to do this 2 more times. Okay. So we've seen this in 5.1, us rolling a die, and we want to find the mean of the number of spots that appears when a die is tossed. And then we want to compute the variance and the standard deviation for the probability distribution. Okay, so here's L1, the outcomes. Here's L2. So remember, this is like when you land on getting, 1 dot, or you land and get, 2 dots, right? Or on a die, you get, right, 3 dots, or 4 dots, 5 dots, or 6 dots, right? So you want to put your data in there, and you see these probabilities are all 1/6. We saw that last time, because this will only of all the 6 possible, there's only one side that has 1 dot on it. Okay, and they call them spots. They call them spots. I call them dots, but they said spots. Okay, so go to turn the thing on, calculator on, go to stat, edit, go to the top, clear, hit enter, come over here to side, go to the top, hit clear right here, and then enter. Okay, so that clears the columns. Okay, then input your data. So this 1, 2, 3, 4, 5, 6, and then over here, it turns out that 1 divided by 6, 1 divided by 6 is actually a repeating decimal. It's actually equal to 0.16 repeating. So you don't have permission, because it repeats, you don't have permission to, oh, I'm going to round this off to the nearest hundreds. You don't have permission to do that, because you'll have round off error. So instead, what you have to do is actually enter the entire, you want to enter 1 divided 1 divided by 6. So I'm going to do that here. 1 divided by 6, and then hit enter. And you see how you get that? Okay, so 1 divided by 6, 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 1 divided by 6. Oh, and you have to be careful. You don't want to mismatch. See how I did an extra one? So I have to go here and clear that. Oops. Clear doesn't work here. So I actually have to delete it, and it takes it off. Yeah. Okay, so you don't want to mismatch, because then you can't get your calculations. I just did I typed an extra one. Okay, so then you go to stat, calculate, 1 variable stats, and hit enter, And then this doesn't change the L1, L2 data. This is fine. Okay, and then calculate. All right, and so now your mean is mu, but you look at the X bar and you see 3.5. And you don't have to round. This is already to nearest tenths. So this is fine. No need to round. So this is already tenths place. So we're good. Okay. Now I'm going to do out of order. It asks for variance and standard deviation. So it's better to do the standard deviation for it first. This was the mean. Should I use mu? Then we're going to do standard deviation, which is sigma, or you can do sigma sub x. See how they do sigma sub x here? That's your subscript, and that's 1.6 1.7078252128. If you had your units, you would put your units, but this doesn't have any units or rolling a die. You want to round to nearest tenths and look at the number to the right. Is that 5 or more? Nope. So it's 1.7. So you round to nearest tenths because your x are whole numbers, or you can say counting numbers. Whole numbers start with 0. So these are whole numbers. You can say counting numbers. Okay. So one decimal beyond that is tenths place. Okay, then we have variance. Nobody's calculator gives you variance. Okay, this is sigma squared or sigma sub x squared. So you actually have to take all of this value and square it to the, raise it to the second power. Okay, so just remind you that here that no calculator provides variance. What you've got to do is you have to square the standard deviation, and don't use the rounded standard deviation. And why? This would be to avoid round off error. Okay. And so when I type this in, I can type it in here. If you do a second quit takes you to a clean window also. And I usually do that if I have a table. But here I can actually just type 1 and then this will clear this. If I just type 1, see, 1.707825128. And then when you score it, you're hitting this X squared key and then you're hitting enter. So this X squared key is, see right here, it's right there. See that? It squares it. And then hit enter. 2.91 us. I was going to put 6 bar, but you see all those 6s and then it doesn't go to 7. To my surprise, it jumps to an 8. So I'm actually going to write those out. Looks like there's 6 of them. But then it jumps to an 8. I was going to put the bar over it, but I'm not because it doesn't have a 7 here, so we'll jump to an 8. So I better put those. But either way, you're going to round to nearest tenths anyway. And then you can look at the neighbor. Is the neighbor 5 or more? Nope. It's a 1, so this stays the same. Okay. Okay, we're going to do one more. On hold for talk radio. So, and notice here how it doesn't have the description. So I think they forgot to put the description for X, the random variables. They did it for the first two. The first two, it was number of trips and then the outcomes. But then here they left that blank. So these are holes for talk radio. So a talk radio station has 4 telephone lines. If the host is unable to talk, like for example during a commercial, or the host is talking to another person, the other callers are placed on hold. So these are, you know, callers on hold. When all the lines are in use, the others who are trying to call in get a busy signal. The probability that 0, 1, 2, 3, or 4 people will get through is shown in this distribution. Find the variance and the standard deviation for the distributions. Okay, we'll also find the mean too while we're at it. So L1 and L2. Okay, this stands for probabilities. These are probabilities. And I just want to stress again from the very beginning that remember what they said here, that this, when we were doing chapter 3, that was raw data, but now in chapter 5, we're dealing with discrete random variables with corresponding probabilities, not raw data. So these are discrete random variables, okay? So these are discrete random variables, okay? Okay. All right, so go to your calculator and let's clear that. So go to Stat, Edit, go to the top, Clear, come to the side, go to the top, Clear, hit Enter. Okay, enter your data, 0, 1, 2, 3, 4, 1800s, 3400s, 2300s, 2100s, 400s. Okay. And just check that we had those correct values. Okay, good. Yeah, it's double checking. Okay. All right. All right. Make sure it's not a mismatch. Okay. All right. So now do stat, edit. Oh, excuse me. Sorry. Stat, calculate, edit, and then one variable stats. So stat, calculate, one variable stats. And then this is fine, L1 and L2. So L1 is your random variables, L2 is your probabilities. Tab down, enter. Okay, and then let's record the mean. And don't use X bar, call it mu, and it's 1.59. And we're going to round that to nearest tenths because this is whole numbers. So you're going to round to the tenths. Look at the right. Is this 5 or more? Yep. So add 1 to it. 1.6. Okay, then I'm going to go out of order. I'm going to find the standard deviation. That would be this. Or like your calculator does, this little subscript there. See that? That's this. 1.123343224. And you're going to round that to the nearest tenths. That the one. Look at the number to the right, which is a 2. Is that 5 or more? No. So this stays 1.1. Okay. And then now we're going to do variance. So I always do standard deviation first and then variance on my paper. And then depending on the computer, the order. Sometimes I think they ask it out of order sometimes. So I do it on paper in order and then I answer accordingly. But variance would be summation squared, excuse me, sigma squared or sigma sub sigma sub x quantity squared. And you're going to have to write this value down. Don't use the rounded off value, because then you could create round off error. So use this value, 1.123343224, and then square it. So see this x squared right here? Okay, and then see, and then hit enter. And this one does, I'm going to put a bar over this because see all these 9s that repeat after. Okay, and then, but I'm still going to round this to a tens place. Then look at the neighbor. Is that 5 or more? Yep, it's a 6. So add 1 to that yellow 2 there, and that gives you 1.3. Okay, then we move on to a new vocabulary that we need for the next page, and it talks about expected value or expectation. That was in our title of a discrete random variable of a probability distribution. Remember, these are probability distributions, okay? And so look what it is. It is the theoretical average of the variable. See, average. The expected value is, by definition, the mean of the probability distribution. And they use this symbol. They use this. They use that. That when you see that, that means expected value. Okay, so this one, I'm going to make a table, and then I'm going to embed my probability distribution in there. Usually probabilities distributions go across, okay, but I'm also going to, on this table, I'm going to make one that goes down this way, okay, and that's going to be needed here. So we'll start with number of prizes. And then the prize. And then the gain, which I'm labeling as X. The random variable, and I'm going to enter this in my calculator as L1. And then probability, P of X. I'm going to call that L2. Okay, so a lottery offers one $900 prize. So one $900 prize. And so the gain would be, you know, you win $900, which is excellent, but then you did pay for the ticket, and it turns out that the tickets were sold at $6 each, so minus 6, and still gives you an excellent profit of $894. And the probability is they're only giving one price like that out of 1,000. It said that there was 1,000 tickets sold. And 1 divided by 1,000 is 0.001. Okay. So you know how I'm going to type this in my L1 in my calculator and my L2. So I have a choice. I can either type 1 divide it by 1,000 and then hit enter. Or I can do 0.001. Either way, the calculator will if I do 1 divided by 1,000, the calculator on its own will change it to this. Okay, then we have one prize of $700, and the gain would be $700 minus $6. That gives us $694. And so there's only one of those. So again, it's 1 over 1,000. Okay. Okay, then you had two prizes that were $300. So each one is $300 minus $6, which is $294. So this one had two tickets, or two of them, two prizes, 2 divided by 1,000. And when I reduce that by 2, 2 divided by 2 is 1. And then 1,000 divided by 2 is 500. And 1 divided by 500 is 0.002. Okay, then we had 4 tickets that were $100. So this would be $100 minus $6 because that's the cost. You know, they had to buy a ticket, or somebody gave them a ticket, but they still had to spend $6. But that's okay. They still gain $94. So this is 4 over 1,000. And if I reduce that, 4 divided by 4 is 1, and 1,000 divided by 4 is 250. And 1 divided by 250 is 0.004. Okay. And then there is one more, because the number of prizes, these are considered all the winners. And of course, not everybody can win. Unfortunately, I hate calling them losers, but there are losers. Like, not everybody can win. And there's 1,000 tickets sold minus 8, 4, 5, 6, 7, 8, minus 8 prizes. That means there's 992 losers. They didn't win. Of course, and if you have to make money, raise money on a raffle like this, so you can't have everybody winning. You got to have some losers, and you're trying to make some money here on this raffle. So on the prizes, there's none, or you can say 0, right? They didn't win anything, and so they actually lost $6. They didn't win anything, and then but they had to pay out of pocket. They bought a ticket, so then they're down 6. Okay, and so this is 992 of them divided by 1,000. And this actually can be reduced by 8. 992 divided by 8 is 124, and 1,000 divided by 8 is 125. And 124 divided by 125, it does terminate 0.992. Okay, so then now what I'm going to do in the calculator is I'm going to enter my random variables, these. I'm going to enter these in L1. And the last one will have to have a negative in there, negative. And then I'm going to enter my probabilities. And I'm probably going to enter just fractions. Probably going to just enter these here. But I already simplify them. As long as they terminate, you can also simplify these. If they didn't terminate and they were repeating, then you can't round off on your own. You'd have to use the exact. And what we're trying to find is, remember, we're trying to find the expectation. The expectation if a person buys 2 tickets. So that's where the E of X comes in, expectation, which is the mean, which is mu. And on the calculator, you know, you use it as AX bar, but you write up as mean. But we want the expectation if 2 tickets, assume that the player's ticket is replaced after each drawing, that the same ticket can win more than one prize. Okay. Find the expectation if a person buys 2 tickets. So it's 2 times that expectation. So it's 2 times mu. Okay. All right, so let's see what that's going to give us. So let's enter your data. Okay, so stat, edit, clear. Okay, let's enter that. So 894, 694, 294, 94, and then -6. The -6, you want to put the negative here, -6. Okay, then 1 divided by 1,000, 1 divided by 1,000, 2 divided by 1,000, 4 divided by 1,000, 992 divided by 1,000. So you see the calculator, we'll see how I did this on paper here. You see it does it for us. See, as long as it terminates, see, it did it for us there. Okay, so then go to stat, calculate, 1 variable stat, so hit enter. And this is good, L1 and L2 is good, so calculate. And there's your X bar, mu, which is a negative 3.4. And then find the expectation a person buys 2 tickets. So negative, this is already rounded to the nearest tenths. So we don't have to round that off. And so we can just put that in here. But if this didn't terminate, it was a long string of decimals, then you should put the long string of decimals in here, because otherwise you have round off error. So you should put the long string of decimals in here and then multiply by 2 and then round off to nearest tens, because otherwise you're going to have round off error. So you should always use the long one, calculate it, and then round off only once. Okay. So 2 times negative 3.4 is negative 6.8. Oh, okay. And wait a minute. I was real quick to box that, but this is actually money. Let me just take that box off. But this is actually money. So it's negative 6.8 is what the calculator has, but it's actually money. So it's actually negative. It's a negative. Put the negative here. $6.80. I should box that instead. Okay, now there's one more page, and you might have to pause the video. I had sent you an email about, you know how I have extra handouts for some of the workbook problems. So this was an extra handout, and So if you printed that, you want to take that out. There was some 5.2 and some 5.3 extra columns that the workbook left out or was a little deficient in. So I usually do these as well. And so you can stop the video and go print that if you need that, if you don't have it printed. Okay. Okay. So let's see. And these are dealing with expectation on top. And then down here, this is very interesting. This makes use of Chebychev's theorem. Remember from chapter 3, Chebychev's? This also uses Chebychev's theorem idea here. Okay. Okay, so a landscaper contractor bids on jobs where he can make $3,500 profit. The probabilities of getting 1, 2, 3, or 4 jobs per month are shown. So X number of jobs, probabilities. So 1 through 4. Okay. Find the contractor's expected profit per month. Okay. So what you would want to do that is find the expected number, which is also the mean of jobs per month. So we got to find that first. And then the contractor should expect, when you calculate that, you would take that expected value, that mean, times the profit. So we're going to find that value in a little bit, times the profit, and you know that's $3,500. Okay. Okay, so let's find it. So let's enter our data, turn the thing on, go to Stat, Edit, go to the top and clear. Come over here, go to the top and clear. Okay, then put in your data, 1, 2, 3, 4. Put in your probabilities, 1/10, 2/10, 4/10, 3/10. Okay. Okay, then go to Stat, calculate, one variable stat, so hit enter. And this is fine, L1 and L2, this is fine. Hit enter. And we get 2.9. And there's no need to round that to nearest tens. These are like whole numbers, counting numbers. So you want to round off to one decimal place beyond, which is the tens, but this is fine. Okay, so we're going to put that value here to find how much the contractor should expect. Now, if this hadn't terminated, were really a long string of decimals, you should use that in here and then multiply times the money and then round that to nearest tens. But this is fine. It stopped at 2.9 times 3,500, and that gives you 10,150. This is money. So that's quite a bit, $10,150. And this is considered the profit per month, expected profit per month. So there's your dollar sign, and this is per month, which is very good. Okay, then we have the number of units or suits. The number of suits sold per day at a retail store is shown in the table with corresponding probabilities. So here's your suits and then the probabilities. And it starts with 19 of them all the way to 23. Find the mean, find the variance, and the standard deviation of the distribution. But then this is interesting. It says, if the manager of the retail store wants to be sure that he or she, right, the manager, has enough suits for the next 5 days, how many should the manager purchase? Very interesting. So this makes use of Chebychev's theorem. We did Chebychev's on chapter 3, and I just changed the X bar mean to mu, and I changed this was the K, X, the mean equals, or mean plus K times S. This is a standard deviation. So I change S to sigma. Okay. And so, and this got chopped off. This is plus 3 times sigma. So that got chopped off. And you know, most of our data, like 75% of our data will fall in this little range between 2 and -2 standard deviations of the mean. But once they fall outside of that, it's unlikely and then highly unlikely. Okay. And so I have a printout of that. I didn't include that on the printout for y'all to print, but that's related to the workbook here when we did Chebychev's theorem. You know, you remember that. This was on page 77. So you see here, 75% of your data fall within this range. See, within 2 standard deviations of the mean. And you see here 75%. Okay. Then this is about 89% when you're about 3 standard deviations of the mean. Okay. All right. So that's where that comes. That's where that comes from, and that's how you can make use of that question. How many suits can the manager anticipate to order? Okay. So first we'll do the mean, standard deviation, and variance. So let's put those in for this problem. So stat, edit, clear, clear. Okay, then enter 19, 20, 21, 22, 23, 0.2, 0.2, 0.3, 0.1, 0.2. Okay, stat, calculate, one variable stats, L1, L2, it's good, calculate. Okay, it looks like it's 20.9. So mean is 20.9, and these are suits. This is not really a unit. This is not really a measurement of length or units, right? But I'm just gonna put suits. Okay, standard deviation is 1.374772. That looks like 0.8. And then we're going to round it to the nearest tenths. And then we're going to look at the neighbor. Is that neighbor 5 or more? Yep. So we're going to add 1 to it. So it looks like sigma is about 1.4. Okay. Okay, now let's do standard deviation. Looks like I forgot about standard deviation. Okay, so you're going to have to take all this value and square it. So 1.374772708, and then squares. You want to hit that X squared button, then the enter button. The X squared button's right here. See? And then enter. Okay. So we get that sigma squared is equal to 1.889 repeating. And when we round that to nearest tenths, is the neighbor 5 or more? Yep. Add 1. So it's about 1.9. Okay, now to answer the question, we're going to do this with 20.9 mean, or excuse me, with 20.9 mean suits. That was the mean. So per day, and a standard deviation of 1.4 suits, the manager should expect to sell between mu minus 2 times sigma and mu plus 2 times sigma. Okay, so those numbers I got from here, right? And then they're getting that from Chebychev. Recall from Chebychev's theorem, 75% of all data values fall within 2 standard deviations of the mean. See, mu plus or minus 2 times sigma. So remember, this was x bar and this was k and this was s. Remember in chapter 3 when we had raw data, but now we have random outcomes. So that's why we're using Greek letters here now. And so mu is 20.9 minus 2 times sigma. Sigma is 1.4. Okay, and then it's going to be 20.9 and then plus 2 times 1.4. Okay, so let's see. So let me clear this. So 20.9, take away 2 parentheses 1.4 close parentheses. That gives us 18.1. And then I'm going to do a second enter. Hit the second button, hit enter. And this is a copy. Then backspace. And this change that minus to a plus sign. And then hit enter. That gives us 23.7. Okay, now, so in order to have enough suits on hand, the manager should order. So what we're going to do is, it says the manager wants to make sure that the manager has enough suits for the next 5 days, enough suits for the next 5 days. So this would be on a low end, this would be on a high end. So let's assume that he's got the max high end. And then times 5 because there's 5 days. Just like a while ago we did expected value times 2 because there was 2 tickets being bought. Well, here it's 5 days. So think of it as 5 times expected value. What's mean? It's like kind of like a mean. Well, it's a mean, but mean with this figured in because of the idea of Chebychevs. So it's 23.7 times 5. Should order 23.7 times 5. 23.7 times 5. So again, you want to use the high end. Imagine you have a good day of selling suits as opposed to on the low end, and then 5 days. So that gives you 118.5 suits. But then you have instructions to round up. Round up your answer to the next whole number. So 118.5 is between 118 and 119, okay? And when you round up, you're rounding to 119 suits. So the manager should have about 119 suits then. That should be enough suits for the next 5 days. Okay, so this is good. Like if somebody owns a business, they don't want to overprice, right? They want to have just the right amount. This is good. And most programs too now, Excel programs and things like that they use have these formulas built in already to them. But it's interesting to see what they use behind that. Okay. Okay, and one last problem that also uses Chebychevs. A pizza shop owner determines the number of pizzas that are delivered each day. Find the mean and the variance and the standard deviation for the distribution shown. And then if the manager stated that 42 pizzas were delivered on one day, do you think that's a believable claim? So we need to figure out, okay, this is just for one day. In the suit problem, it was 5 days. So here we're going to multiply it times one day. one day as opposed to 5. But when you get your answer and you round up, you're saying, okay, is it reasonable? So are you falling in here, or are you falling like here under unlikely or highly unlikely? So where do you fall? Or is it like totally out of the range? If it's beyond this range, if it's beyond that range, then forget it, and it's impossible. So you want to see, is it, certain, pretty in the certain area, pretty likely or unlikely, likely or unlikely. Okay. So let's put these in, put this in L1 here and L2, find the mean and the standard deviation, and then I keep forgetting the variance. I left off the symbol for variance there. Okay, so let's do that. Stat, edit, clear. Okay, input your data, 36, 37, 38, 39, 40. Input your data, 1/10, 2/10, another 2/10, a 3/10, 2/10, okay? And it's equally yoked. You want to make sure you have enough. You want to equally balance, otherwise it won't calculate that correctly, or won't calculate at all, probably, if it's not equally balanced. So go to stat, calculate one variable stats, and this is fine, L1, L2, and voila, mean is 38.3. So you don't have to round that off. And this is not really units, but I can put pizzas if you want something there, but it's not a form of a unit. Okay, standard deviation is, see all of this here. And then you can round that to nearest tenths. Look at the number to the right. Is that 5 or more? Yep, it's a 6, so add 1. So that's about 1.3. Okay, and now you need standard deviation. Excuse me, now you need variance. So this one was standard deviation. So now you need variance. Just sigma squared. You can do sigma squared, or you can do sigma sub x squared, okay? All right, either or. So you have to type all that in. And then square it. And then square that, x squared. Then enter. And then round that to nearest tenths. Look at the number to the right. Is that 5 or more? Nope. So it's 1.6. Okay. So this mean is for this. That's your mean right there. Okay. Okay. Now, and look what they say. Look what they reason. They do say that it's possible. 42 pieces. It's possible, but to be delivered on one day. Maybe it was a special day like Super Bowl Sunday, or maybe election day or something, right? Maybe something on one day, an important day. But it is, they say, highly unlikely. So it's in the highly unlikely. So I think it's unlikely. I think they're saying highly unlikely, but I think it's under unlikely. But it's still possible. It's not like they said like 500 pizzas. If they said 500 pizzas, that would be impossible, right? But it seems like it's going to be reasonable, and you'll see that when you start seeing the numbers come out, the numbers. So and it says here that according to Chebychev's theorem, 89% of all data fall within 3 standard deviations of the mean But beyond this limit, then it's highly unlikely to occur. Okay, like almost impossible, right? Almost, it's over that. So this got chopped off, but this is a 3, and this is sigma. So I calculate on the high end, just like I did over here on the high end on the suits. A good day, I did the high end as opposed to the minus. So I look at that also. The mean here was 38.3 plus 3 times sigma was 1.3. I'm getting 42.2 pieces. And remember, if I multiply it times 1 day, earlier in the suit problem was 5 days. This is just on 1 day. That gives you 42.2. But remember, you have to round up. So when you round up, 42.2 is between 42 and 43 pizzas. So you see when you round up, it's about 43 pizzas. Okay, and so that's at 3 standard deviations. That's at 3 standard deviations, 89% of your data. Okay, will fall within 3 standard deviations. So that's why you see here's your mu minus and mu positive, and over here we're hovering over here. Remember mu plus? We're hovering over here at above, like at 43, right? 43 pizzas. Yeah, so you see, they said 42 pizzas, and already at 43 pizzas, we're over here under the highly unlikely. So it's possible. It's not like they said, how about if you got 500 pizzas? So 500 pizzas is way off from 43. So I would say, yeah, it's possible, but it's unlikely. And let me see if I do mu plus 2 times sigma, let me just see what that is. If I do mu plus 2 times sigma, let's see where that puts me. Let me put that here. If I do mu plus 2 times sigma, the mean was 38.3 plus 2 times sigma, which is 1.3. Let me see where that puts me at. So I'm going to do a second enter, which copies that. I'm going to backspace. And I'm going to just change that 3 right there to a 2. So I don't have to do all this typing again. And that gives me at 40.9. And when I do 40.9 times 1 day, that gives me 40.9. And then when I round up, let me see, where can I put that? Right here. 40.9 is between 40 and 41. So 40.9, I'm going to round up to 41 pizzas. Okay, so that was at, see, 2 standard deviations. So you see right here, see 2 standard deviations right here. This is 41 pizzas. Yeah. So at 41 pizzas, this was 41 and this was 43. This was 41, and then this one down here gave us 43. Yeah, and then they said 42. So you see 42 pizzas is in this realm. So it's definitely possible. And you can argue that either the adjective, you can argue with it saying that it's you can argue saying either that it's unlikely or that it's highly unlikely. Yeah, you're in the ballpark over here, because this was 41 pizzas. This was 43 pizzas. This work gave us 43. This work gave us 41. So yeah, you're in this ballpark. So it's likely, but it's either you say unlikely or highly unlikely, because we're talking about 42. Okay. Okay. So I hope that makes sense. And work on your homework for 5.2 then. Okay. Good luck with that.